So what I'm going to talk about is a result in done in collaboration with Eduardo Serpa and Emmanuel Quepo. And yeah, I think it's going to be a little, maybe it's a little different from what we've seen so far in this session. Okay, so I prepared something very self-contained. So I hope everybody can follow, and I will then try to highlight the main the important things about our work without going into much detail. Okay, so well, let us begin. So first, I'm going to give an introduction, maybe a not too short introduction about the control systems and the controllability and observability duality, and a little bit about systems. Okay, and then I'm going to talk about our work, which is over the generalized Hirota-Satsuma system. Okay, so in general terms, a control system of PDEs can be formulated as, in general, as evolution equation, okay, where we can act on the system via some parameter, okay. This parameter is called the control, okay. And here Y is the state of the system, which depends on the time t, okay. And usually this state for every t, the state lives in a functional space, okay. So the problem, the controllability problem is the following: given an initial condition, okay, and a final time t, a capital T, okay. The question is if we can we find a control, a function that we can inject on the system in such a way that the state of the system goes where we want for a given, for instance, a given target Y1, okay. So the condition is that our state in capital T equals a Y1. So basically what we're saying is that, okay, we have our initial condition over here, okay. So if you let the system evolve naturally, if you do nothing, okay, in your time window, okay, you end up over here, for instance, okay. But you have a target that is over here, okay, for instance, Y1. So you want to drive the solution of your equation to that state, okay, in capital T, okay. So the question is that, can we find a V, a control V, such that the solution associated for that function, for that control, matches the final state, okay. And okay, and depending on the equation and what you and what you're trying to do, there are different kinds of controllability. This one is the exact controllability type. You can also consider null controllability, where the final state is the null state, which I will talk about later. Okay, or maybe you just want to go close to your target, okay, in a neighborhood, for instance, of your target. You don't need to go exactly there, okay. And sometimes, usually for nonlinear equations, what you can obtain are local results, in the sense that you need to start very closely to your final states, okay. And okay, so to introduce the control of PDEs, let me talk about let me tell you about the one of the simplest examples, okay, which is the heat equation, okay, posed in a bounded domain. So we can imagine that, for instance, we're in a room, and you have a device that you can manipulate, right? Like, for instance, the air conditioning. So you can cool or heat the room, okay? The temperature distribution, of course, is given by the solution of the heat equation, okay? And our control is going to be a force term, a source term, right? that we can manipulate. Okay. Here, actually, we're gonna assume that, of course, we don't act on all the omega, okay, all the domain, but only in a small part that we call omega. Okay. So the control acts only on this part of the total domain. Okay. And we ask ourselves, okay, given a time, a final time, and an initial condition, and a final state, okay, can we find a control such that our solution matches that final target? Okay, and in general, for the heat equation, due to the regularizing effect, this is not true for every final state. Okay. Actually, for the heat equation and in general for parabolic equations, it's more natural, or it makes more sense to consider another notion of control, which is the control to the trajectories. That is, we look to drive our solution to a natural state of the equation. Here, what I mean by that is that we take the heat equation without a control. Okay, so our target is the solution of this equation without control at time t. Okay, and that is the control to the trajectories. Okay, but actually, given the linearity of the equation, by taking the difference between the control equation, which is given by y here, and the y bar, which is the natural, the free trajectory, okay, this is equivalent to the new controllability. Okay, so the new controllability is to look for a control such that drives our solution to the null state at time capital T. Okay, so we're going to concentrate on this case. Okay, to drive our solution to the null state. Okay, now for this equation, there's a way to construct the control, which is done by a duality method with which is called the Hilbert uniqueness method. Okay, so the idea is to multiply our equation, the heat equation, which is here, by phi, which is the solution of this backwards heat equation without control. Okay, and this is called the adjoint equation. Okay, and this actually, after multiplying the solution of this equation by our control equation, okay, and after some integration by parts in space and time, we can actually find this relation between the our variable, our state, okay, the control, and the adjoint state. Okay, so from here we can actually find a characterization for the controls that drives the solution to zero. Okay, we just observe here that if you want our state to be zero, we just put zero here, and we find that actually a control such that drives our solution to zero has to satisfy that this part of this identity is equal to zero for any initial state that we give to the adjoint equation. Okay, so this is the characterization actually for the new controllability of the heat equation. Okay, and that actually this can be done in more general settings, and is what we are going to do later on. Okay. Okay, so actually this characterization, this identity, okay, can be seen as a first order condition for optimality for the following functional, okay, which takes the solution for the solutions of the adjoint equation. Okay, and actually this functional, we can prove that it's convex, continuous, and it will be coercive, okay, if there is there's a constant, positive constant that is independent of the joint system, the solution of the joint system, such that this estimate holds. Okay, and this is known as the observability inequality. Okay, for the adjoint equation. Okay. Okay, so if we can prove such an inequality, which actually what it does is that, what it says actually is that we can estimate the final state of the adjoint system, okay, by a local term of the solution of the adjoint system. Okay, by local I mean that we only are able to look inside the control domain, which I recall it's only acting on a small part, right, of the this is the big omega, little omega is over here, right? So we're just observing the solution of the adjoint system here, okay, but we can obtain information on all omega, okay. That's essentially the observability. Okay, so given this observability inequality, we can ensure the coercivity of this functional, and we can ensure that has a minimum. And actually, since the previous condition of the characterization of the control to 0 is a first order optimality condition. Okay, the control we take the control as the minimum of this function. Okay, so so we reduce actually with this duality method, okay, to look for a control, we reduce the problem of existence to the proof of an inequality for the adjoint system, okay, which is more accessible, but it doesn't mean that it's easy to prove. Okay, so the key element here is to be able to prove an observability inequality for the adjoint equation of the system that you're trying to control. Okay, and actually one can prove that the new controllability is equivalent to the observability inequality. Okay, so the task now is to prove this kind of inequalities, which, as I said, is not a trivial thing. Okay, because you have to observe in the whole omega just by a little part of the whole domain. Okay, so we need something that concentrates the information here in the little omega. Okay, and for that we have available for us a very powerful tool. I mean, there are several techniques to prove this kind of inequalities, but one of my personal favorites, okay, are Carleman estimates. Okay, which actually looks like, for the heat equation, okay, it looks something like this. It's a let's say an estimate which estimates on what the energy of the adjoint system, okay, in terms of the operator, okay, and a local term. Okay, of course, this kind of estimates is not a unusual estimate. It's not an usual energy estimate. It's a weighted estimate. Okay, where here we have some weight functions. Okay, which are positive. Okay, and but with the characteristic that the critical points are only in the included in the little omega. Okay, so that allows us to let's say concentrate the information where we want. Okay, so these wave functions, I'm gonna maybe put a little picture here. Okay, let's say this is omega. Let's say this is This is Rn, for instance, okay? And the little omega is here. So these wave functions are something like this, are positive, okay? But the, oh, that's not a very nice drawing, maybe that's better. Okay, this should be the control region, the little omega. Okay, and yeah, the critical points are only, which are here, right? Are included right there. So this this allows in a way to send the information. Let's say that's how I see it. To send the information, to concentrate the information at the control region, the little omega. Okay. But what is important here actually is that this kind of estimates, which to prove it, they're actually very technical. Okay, they require a lot of computations, but they give us essentially the term that we need for the observability. Yeah, the local term, the observation in the little omega. Okay, so finally, to deduce the observability, we use this kind of estimates. Okay, and we combine it with some dissipation properties to obtain dissipation properties of the heat equation. Okay, to obtain something like this. Okay, to recover from this integral, for instance, the final state of the adjoint equation. Okay. So that is a quick overview for the heat equation, but gives us a general idea of what we have to do. Okay, we have to look for the appropriate observability inequality, which is given usually for a suitable Carleman estimate. Okay, now let us complicate a little more this problem, and let us consider the problem of control of two heat equation. Sorry, okay, and actually we are going to look to control the two states, okay, using just one control. Okay, so we see here we have two heat equations which are coupled, right? The second variable acts on the first equation, and the first variable acts on the second equation, right? But we only act through a control, okay, on the first equation. So what we're looking for is to control to zero this equation at time capital T. That means only with one control we want to drive both states, Y and Z, to zero at capital T. Okay. And of course, here it doesn't. The fact that there's no control in the second equation, it does not mean that we're not controlling it. Actually, what we're doing here is like with the control V here, we control Y, right? And through Y, we act on the second variable, okay, the second state, okay. And here, using the same idea, the same duality approach, we can prove actually the observability inequality that we only observe the first state of this system. Okay, we can see here that actually the first equation is related to the first state, and the second equation is related to the second state of our equation. Okay, so the fact that we can, if we are able to observe just the first state of this adjoint equation, okay, that will allow us to define the control B, okay, and control both equations without the control on the second equation, okay. And okay, and so what's the idea to the general idea to do that is actually we have, as I said before, observability comes usually from a Kahneman estimate, and we have one for the heat equation. So we have a Kahneman estimate for each kind of the for each one of these equations, okay. So we used a Kahneman estimate for each one of those equations, and we combine them, okay. And actually, the way function can be chosen. So once we sum up these two equations, these two inequalities, sorry, okay. The weight function that is here is much smaller than the ones that are on the left-hand side. So we can neglect these two terms, okay. And we end up with only two local terms in the little omega of the two states, okay. But we want to get rid of the second one, okay. And for that, we use the coupling between the equations, okay. And using the first equation, we see that the second state of the adjoint system, okay, is related to the first one in that way. So basically, what we do is here, okay, in this local integral, we use the equation, okay, in this way, for instance, and after some computations, okay, we can estimate, we can transform, let's say, this local term of psi, okay, only in a local term of phi, okay, and in that way, we can get rid of this local term, okay, just using the equation. Okay, so that's the general idea for the control of systems, which actually we will apply for our work. Okay, so now let me just introduce the system that we work on. Okay, which is the so-called generalized Hirota-Satsuma system. Okay, which I think which was introduced by Hirota and Satsuma in the 80s. Okay, which consists of three coordinate diversity or KDV equations. Okay, it's a nonlinear system. Okay, and actually this system generalizes a system of two KDV equations, which was proposed by the same authors. Okay, and this system actually describes the interaction of two long waves with different dispersion relations. Okay, and most works actually have been focused on the existence and conserved quantities of this system. Okay, and up to our knowledge, this was the first attempt on controlling the system. Okay, now let me show you what is actually the control system that we propose to study. Okay, and actually we will take the generalized Hirota-Satsuma system, which is the system with three equations. Okay, in a bounded domain. Okay, so we need some boundary conditions and some initial conditions, which are here. Okay, and we're going to consider two controls acting on the second and the third equation. Okay, so what we're trying to do here, of course, the controls here, so I call them P and Q, which are distributed controls, which are acting on subdomains of a given interval, which I call here 0L. Okay. Okay. So what we want to do is to control the system in this bounded interval, and I just want to say here quickly that with this in this setting, with these boundary conditions, which are the usual ones for the for when we're taking the PDB equation in an interval, the system is well posed, at least for small data, okay, at least for small initial conditions and small controls here, okay. First, of course, in a suitable norm, okay. So, some remarks about this control problem that we're proposing is that, as I said before, we seek to control 3 equations with only with 2 controls, sorry, acting on the second and the third. Okay, and one of the reasons that we chose this system and the location of the controls, right, is that we can act on the first. We don't consider here in the first a control in the first equation, because we're going to act on that state through this coupling, okay, which is actually which is a more complicated coupling that we saw before with the heated equation, because it's of first order, okay. The coupling, it's through the first derivative of the third state of the system, okay. The controls act on 2 different independent subdomains of the interval, but here, due to technical issues, we are going to assume that the second subdomain, little omega, touches the boundary, okay, of the interval, okay. So maybe a little drawing here. We have our interval here, okay. So we can take for instance, this to be the control region for the control P, okay. But for the control Q, okay, we're going to ask that touches that is located at the right end of the interval, okay. This is where the control Q acts, okay. Now, in principle, they don't have to be disjoint, okay. They are arbitrary, okay. And I'm going to try to explain why we need this assumption, okay, later on. Okay, so what our result here establishes the local null controllability for these states. That means that we take initial conditions, okay, and small enough. If we take our initial conditions small enough, okay, for instance, in the L2 norm, we can find controls P and Q which act on these 2 subsets, okay, such that the solutions U, V, and W of our system go to the new state at capital T, okay. And the idea is to use the duality argument that we saw before in this setting, of course. Okay, so I'm going to show you what is the general strategy that we follow to prove this local null controllability result. Okay, and it's the following. It consists of mainly three steps. Okay, the first step is linearization around the origin. Okay, basically we linearize around 0. Okay, so we end up with a linear system, okay, where we add some source terms, okay. These source terms play the role of the nonlinearities, basically, okay, which are written down here, okay. So the second step is to prove a new controllability result, okay, for the linear system, okay, for any given source terms that we put here, okay. And then we recover the result for the nonlinear system, the original system, right, using a local inversion argument, okay. And actually, just to show you here, what we do is to try to locally, let's say locally invert this operator, okay, which goes from it goes from two weighted binary spaces. So basically, what we do is we take the states and the controls, okay, and we write here the components of this functional, okay, are just the equations, okay, that we want to solve, okay, and this weighted Banach spaces where the solutions and the controls live are such that our solutions decay to 0 at capital T, okay. So to the key points here to prove the result is that we can prove actually that this function is of class C1, and we need to prove also that the derivative at the origin it's surjective, okay, and that is equivalent to the to find to a new controllability result, which is the step 2 of this strategy, okay. So basically what we're saying here is that this one right here will be F1, right? This one right here will be F2. This one right here will be F3, okay, and this one are the initial conditions, basically. Okay, so the new controllability, which is the step 2 for this linear system, will give us the surjectivity of the derivative of the at the origin of the of our function, so we can invert locally around the origin. Okay, so we concentrate on the second step, which is with the main part of the work, okay. And here I'm going to show you just briefly how we prove the observability inequality, okay? Because to prove the control result for the linear system, we're going to use the duality approach that we saw earlier. Okay, and well, actually here I just want to remark that following this approach, which is linearizing around 0, we observe here that the linear system, that the second equation becomes independent of the others. Okay, in the sense that the second state, which is V, does not interact with the first and third equation. So actually, the control P is needed here. We cannot remove it. Okay, so in this sense, our result following this approach is optimal. We cannot remove more than one control of the system. Okay. Okay, so we can prove that actually the adjoint system for the linearized system, okay, is given by again three backwards KDV equations, okay. And what we need to do actually is to prove a Kahneman estimate or an observability inequality, if you want, just observing the second and the third state of this system. Okay, so something like this. Okay, where we only need to have local terms of psi and eta in this case. Okay, that's the main thing. So how do we do that? We have a Kahneman estimate for the KDV equation, okay, available in the literature. Here are some references actually. Okay, and one of the differences first is that I mean, we follow the same approach. We apply for each one of these equations, a Kahneman estimate for the KDB equation. Okay, so basically here we will find here the functions G are there. Okay, and one difference with the heat equation is that we have an extra term when we are looking for a Kahneman estimate with an internal observation. Okay, we have this additional term which involves the second derivative of the state. Okay, but actually this can be estimated. Okay, so let me just cross it. Okay, this can be estimated using the regularity of the solution. Okay, then we end up with 3 local terms. Okay, for each one of the states, and we want to remove this one. Okay, this is the one that we don't want, and we do it exactly like we did before. Okay, using the equation. If we see here the third equation, we see that the component 5 of the adjoint equation can be written in terms of eta, which is a good term for us. Okay, but the thing is that the coupling happens at the first order. Okay, and since we have that little omega is included in the interval, we don't have Poincare inequality, if you want to. We don't have here in this integral homogeneous boundary conditions to estimate the norm of phi in terms of the norm of phi x. Okay, so here is where we need that the little omega touches the right hand side, for instance, of the interval, so we can use the boundary condition, and in that way we transform this integral in a similar integral but involving the derivative, and now we can use the equation just as before. Okay, like this, to transform this integral of phi in a local integral of eta. Okay, and that is the main idea. And actually, this is the only place where we take where we need that the little omega touches the boundary. Okay, this geometric assumption. Okay, so just to finish, let me give you some final comments on this work. Okay, as I said before, following this strategy around linearization, okay, it is not possible for us to remove the second control. Of course, one wants to control a system of equations with the less controls possible. Okay, but in this case, following this approach, we cannot, or we are not able to remove this the control P. Okay, now a possible solution for that is to use the nonlinearities. Okay, to control the states. Okay, where, for instance, we remove the control P here and actually use the nonlinearity to control that equation. Okay, but it's something that we haven't explored yet. Okay, but there are arguments like Coron's return method to use the nonlinearity to control the equation. Okay, and actually, as I said before, the assumption that the little omega touching the boundary, actually it can touch either side of the boundary of the interval. Okay, it could be in 0 or L. Okay, but it's only technical and it's only used like I showed you before. Okay, it's only used there. Okay, but recently there is an improved Kahneman estimate. Okay, used for another problem. Okay, but can be adapted to this case to consider the more general case without this geometric assumption. Okay, and with that, I finished my talk. I thank you again for the invitation. For me, it's always a pleasure to be around you, even if it's remotely. So thank you very much.